Hello, so I'm a student who's doing the chemistry side of the AI efficacy study. Um, this is sort of a bit of an awkward situation because I had just completed I was assigned to do version B first and then version A. So I just finished version B here, um, and I was basically halfway through. I just started on the guided tutoring, and then the power went out, and then my recording was lost. So I'm just going to sort of walk through or give like a high level overview of my thought process for this initial first exam, just to sort of try and make up for the lost footage. It is quite sad. I did talk a lot, give lots of my thoughts while doing the exam, but unfortunately, I wasn't able to recover the video file that was lost during the power outage. There's just this massive thunderstorm outside right now, which might be some kind of indication. Maybe something hit the power grid or something. But we're back, and I'm just going to first, I'm just going to set, it doesn't particularly have to be 20 minutes, but I'm just going to put on a timer there and then start talking about this quiz and sort of my thought process when I was doing the questions, exactly how it was when I didn't know the answers. So I'm just going to jump right in, review the entire exam. Maybe not take the full 20 minutes. So might be a bit of a more condensed sample. Maybe it totals up to only an hour because of some skipped sections. But if we start off with chemistry B, this first question, the IUPAC naming, I basically counted each of the carbons, each of the possible chains. So alpha to beta, alpha to epsilon, alpha to gamma here. So this is 8, this is 8, this is 9. This reverse S shape here from alpha to epsilon. And so that helped me answer the first question. There are 9 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9 in the parent chain, and that makes it called nonane of because that's the abbreviation for this hydrocarbon. And then to determine numbering, I particularly said, I remember saying that numbering will begin at the carbon. So it's going to be either alpha or epsilon, right? So it's going to begin at the carbon with the closest side chain. So counting from alpha, we have 1, 2, 3, 4, 5, and we come across this propyl group side chain here. So that's the 5th carbon, but if we count from epsilon, we have 1, 2, 3, 4. So on Z there, you have a methyl group. And so because 4 is less than 5, we're going to start naming the molecule at epsilon, carbon. And so that was correctly deduced. Consider possible branches at carbons X, Y, and Z. Okay, so the branches at carbon Y, this is just a knowledge-based question, whether you know that this is a propyl group at carbon Y. If you correctly identified the molecule, then you would have correctly identified the propyl group here. So I put propyl, and then which carbons can only make one bond. So for this multiple choice question, they gave primarily X, Y, and Z. And so I basically looked at them and their availability to make further bonds given their current capacity. And so I realized that since the X carbon is only bonded to 2 other chains, there are 2 available spots or opportunities for bonding here. While on the Y carbon and the Z carbon, since 3 of the 4 spaces on the carbon are filled for each of these letters, that's the correct choice for the one that can take only one more chain or one more branch, whereas X is with 2. So that answers the next 2 questions. So one more bond is Y and Z. 2 more bonds is X. And then when approaching the IUPAC naming convention for this molecule, I put 4-methyl-5-propylnonane. And so this was deduced because I think my thought process was that M was alphabetically comes alphabetically before P, so methyl versus propyl. So I identified the methyl first, and so if it were an ethyl group instead, you'd have to say ethyl instead first. But it's a propyl group, so we say methyl first because P comes after M, and so to do that, we count from the first carbon, the epsilon, as we've previously identified. So 1, 2, 3, 4. So on the fourth carbon, we have a methyl group, it's just a single chain, and then on the fifth carbon, we have a propyl group, which is a chain of 3. So going in alphabetical order, we have 4-methyl dash 4-methyl dash 5, because it's the fifth carbon, propyl, and then directly on to the back of propyl, we just tack on nonane because of the 9-carbon long parent chain here. And also it's just a single bonded, completely, just an alkane through and through, branched alkane. And then the addition of a methyl group onto carbon blank and blank would add an extra side chain. And so I realized that none of the answers can contain the first or last carbon, so alpha and epsilon in this case. And so A, B, and C all contain some kind of version of this. So if you can't really have this. It's instead of an extra side chain, it would be, it would just extend it from nonane into decane by adding a methyl group, so it wouldn't be a side chain. And so I just picked the only one without alpha or epsilon, which was delta and theta here. Delta and tau. And yes, so it would make sense. 1, 2, 3, a methyl group on the 3, so it would be 3,4-dimethyl 5-propyl nonane. Or if I were to add one here, on the 7th carbon, it would be just whatever that would be. But overall, it doesn't change that it's a 9-carbon long chain with 2 more methyl groups on the delta or the tau there. And so, which of the following molecules is not an organic molecule? I deduced carbon dioxide because just CO2, there's no carbon bonded to hydrogen. In these two examples, that is present. I'm not entirely sure about the formula for methoxide, but carbon dioxide immediately stands out to be the inorganic molecule here. And the valence electrons question. So for the valence electrons question, I was sort of a bit confused. I misconstrued that the valence electrons were the same as the number of electrons for some reason in each hydrogen, and I said just because there's 4 hydrogens in methane, there must be 4 valence electrons, which was incorrect. I forgot to count the valence electrons for carbon in the molecule as well, and so it should be, so I picked 4, I guess. I might go over it a bit later in my study session emulation, but here it is. I picked 4. And this also sort of messes up the chain for the next question as well. Which element has the same number of electrons as methane has valence electrons? So I thought, since it has 4, beryllium means 4. Beryllium's the 4th one, so it should be beryllium. But that was incorrect because the answer was 8, which makes it oxygen, because oxygen is number 8 on the periodic table. I also had a misunderstanding. For some reason, I thought oxygen was 16 electrons instead of 8, but So I confuse the molecular weight with the number of valence electrons, but sorry, with its atomic number. But the correct answer should be oxygen here because it's 8, and it has the same number of valence electrons as methane here. So the following functional groups is most likely to taste sour. I put RCOH because this is the carboxylic acid group, and it's in the name. The acid makes it so that it is an acid. I mean, the pH is less than 7, and these kinds of compounds are sour tasting. It's just a physical property. And then for this written response, I put, can your answer to the previous question participate in hydrogen bonding? Okay, so I put yes, it can because of the OH group, because in the presence of the hydroxyl group, yes, making the molecule qualify with the correct functional group such that it can participate. Okay, maybe I shouldn't have added this section at the end, but overall, I think I just answered because there's the OH group, it qualifies it for hydrogen bonding, and it seems to align with the answer here. Which molecule have the lowest boiling point? Okay, so I spent a bit of time on this one. I immediately sort of took out the methanoic acid and the I don't know what that one is. Ethanoic acid? No. It's some kind of ester or something. But I immediately took out these two because I saw they had these more complex functional groups. First of all, like the presence of oxygen makes it so that there's like hydrogen bonding in this one, or just higher London dispersion forces with a larger molecule here, right? So I eliminated that one, and I was deciding, I was stuck between CH4 and CH3Cl. So chlorination or not. And so basically I came to my answer because I said the chlorine was a larger molecule compared to just an additional hydrogen. So the LDFs in this molecule D would be stronger than B, so that's why I picked B. And then this, how many hydrogen atoms does a alkane have? This is just 2n plus 2. I just use the example of the methane here. So C, one carbon atom times 2. 1 times 2 is 2, plus another 2 is 4, so it lines up. So this alkane with 1 carbon atom should have 4, and that's the case for all other homologous series for the alkanes here. Okay, moving on to what other sections are. Okay, I gotta speed up here. So this next section is just properties of these organic compounds. Basically, it gives you this, and then a few questions about its properties. Molecules can partake in dipole-dipole interactions. So dipole-dipole interactions, I recognize that they are based on polarity, right? So only the polar molecules will have dipole-dipole interactions. And so I picked diethyl ether, methanoic acid, and decanoic acid because they're the only ones that are like they have functional groups, while methyl cyclopentane doesn't really qualify because it's just a complete hydrocarbon, and it doesn't have the same sort of qualities as the other ones do. It's still going. So I picked this one. Originally, I had selected all of them because I was a bit confused. I thought the methyl group on cyclopentane made it a bit more polar, but that was not the case. They have the same electronegativities. Assume each substance is liquid at room temperature. Which of these molecules is a mix? Okay, so again, I put the alkane because of the fact that because of my answer here that I selected, I chose this because if you choose this, you're saying that these three molecules are polar, but methyl cyclopentane is not. So because it's nonpolar, and this tetrafluoromethane is also nonpolar because it's the perfectly I don't know, its structure just points to the fact that it's nonpolar. Um, doesn't have any polar groups or molecules here. It would mix with tetrafluoromethane, the methyl cyclopentane, because they're unlike each other, right? So because both of them are nonpolar, I put my justification for the next question, the next written question was methyl cyclopentane is polar and so is CF4. I should have written on top of this like dissolves like as written in the answer here, but I was thinking that when I was writing the question, so that's how I did this one. And then next question, despite that methanoic acid has fewer carbon atoms, its boiling point is much higher. And so methanoic acid, yes, okay, so this is just the difference in properties between functional groups and typical hydrocarbons. So because methanoic acid is a carboxylic acid, it is near the top of the hierarchy for these organic molecules, and thus it has hydrogen bonding, it has dipole-dipole interactions, it has dimerization, it has some sort of LDFs, not very strong, probably the weakest LDFs in this whole selection, but its other intermolecular and intermolecular forces make up for the fact that it's a smaller molecule compared to methyl cyclopentane, so that's why. That's why I selected, what was it? If for this question, participate in hydrogen bonding. Yeah, that's one of the big intermolecular forces. Where would you expect butanol to place on this list? So I was running out of a bit of time here, so I quickly just selected this one. My logic was butanol I was looking primarily at the size of the molecule. I just completely skipped over the fact that it's an alcohol and not a hydrocarbon. So I think that was why I got this one wrong. I think in my mind I thought I read butane, so I put it there, but because it's butanol, should be between these two, methanoic acid, decanoic acid. But yeah, this is just a bit of a time crunch question. And then this next one here, excuse me. So we're given this hexane molecule here, 1, 2, 3, 4, 5, 6, right? And so it asks the addition of a methyl group to which carbon would not produce a molecule with a side chain. This was sort of a misunderstanding I had with this question. I did this really fast. I thought it asked which would produce a molecule with a side chain, and I thought, I don't know, I think I was just doing it very fast, but I just saw beta here on the a bit of a odd position compared to the more symmetrical alpha and gamma, and so I just picked it. But the answer is all of them should produce a side chain molecule. Yeah, because no matter where you add a methyl group, this will become a side chain, this will be a side chain, and the methyl group you add itself will become a side chain for beta here, and so it should be all of them. The addition of a methyl to which carbons would produce the same molecule? My thinking for this question was, because it's symmetrical, alpha and gamma, like if you just like flip it around, if you just flip it horizontally along the horizontal axis, it would just be the same molecule. So I picked that one really fast. And then for this question, at this point, I had not a lot of time left, so and like the first time I did this quiz, I wasn't very conscientious of the process for determining valence electrons. I was a bit cloudy on that concept, and so I put 14 because I counted 1, 2, 3 spaces on the carbon twice, so 3 times 2 is 6, and then 2 spaces on the carbon for 1, 2, 3, 4 carbons, so 6 plus 2 times 4 is 14, and that gives all the valence electrons just for the hydrogen groups that are on this molecule, instead of the just the hydrogen groups, right? And so I neglected to count the, I'm just gonna pause the timer here. I'm just going to talk over. I neglected to sort of consider the carbon atoms. Right, yeah, I didn't count the carbon atoms' valence electrons for this question, which is why I only came up with 14, but yeah, that's why I put 14, just the hydrogen's valence electrons, unfortunately. What is the maximum number of propyl groups that we added to carbon? A, alpha. And so again, because this carbon has 2 more bonding opportunities, I put 2, because it's only bonded to 2 more branches right now. So it has 2 free slots per se, because carbon has 4. So I put 2. And then last section, the electrons in a benzene molecule are not fixed on one atom. They are, I put covalent. This was my last-ditch effort. I had a couple seconds left. But I don't know why I put covalent. I think it was the concept of sharing bonds that sort of led me to put covalent here, but it should be delocalized. Benzene, of course, drawn with a hexagonal alkane with the circle in the middle means that it's sharing electrons, C6H6. And then for the last question, so yeah, this question was just I guess just a knowledge issue. I didn't realize that should be this one. And then the last question was about identification of compounds. And so I read, so it gives you a bit of a description about the compound that it's asking, and then it asks how would you attempt to identify it, right? So immediately I'm looking at there's 2 titration options, one like dissolvability option as well as one dye option, and so I read immediately a neutral dye, right? So when I'm making I originally was looking at titration because titration is usually used to actually I'm not sure, I shouldn't say that, but I was immediately looking at titration because it was 2 of the options. But once I read neutral, I was thinking adding HCl or NaOH won't really help to determine this, right? Because it's a neutral solution. What will that do, right? You're not neutralizing a neutral solution, and you're just going to acidify a neutral solution. So it'll just be, this doesn't tell you any information. And so I read the second point, it is polar. And so this is a lot more useful to me piece of information because you have, it is polar, right? So you're asking it how to identify it. Like dissolves like, right? We saw in that previous question. So if we add water, a polar compound will readily dissolve in water. That makes sense, right? So polar and polar, so I put that feels like it makes sense. And again, maybe this one, add orange dye, artificial orange dye will absorb into the compound. That doesn't seem very right. I'm not sure what kind of compound would qualify for this, but that's how I did this last question, and I ended up scoring 17 out of 25. But maybe if we add up the written questions like this one and that one, I think that's all of them, I get something like 19 out of 25. So I moved on after that. So next in the study instructions, I'm just going to move through as if I was doing it the first time, but we just did chemistry version B, and moving on to the guided tutoring. I already had a sort of a extensive conversation with Gemini here. How would you determine the number of valence electrons in a compound okay, sorry, I'm just reading through your autopilot right now, but for this 30-minute free study session, I just basically asked the model about some inconsistencies in my conceptual understanding. So that would be the concept of valence electrons for compounds instead of individual elements, right? It just completely skipped my mind how to count these valence electrons. So I clarified that and just basically pasted in some of these questions I got wrong, um, such as this one, uh, and going over the quiz again to sort of learn the concepts. Not so much like, yeah, yes, I guess just to learn the concepts for each question so that I can use them in the next quiz. Um, and then yeah, I just went through the quiz, put through, clarified some stuff, and at the end I also asked. Wait, I'll just scroll through the conversation. So conceptual question. I pasted the question. Another conceptual question. Um, I had a big sort of, I wouldn't call it a eureka moment, but maybe I had a bit of a realization that I was trying to count valence electrons with orbitals and filling electrons like that instead of just the more like simple like junior high school method of counting through shells. So like look at this question, right? Given atomic number 16, how would you fill the orbitals? Because I thought orbitals were, oh, I'm so sorry. Okay, I thought orbitals were filled 2, 2, 8, 10, right? Um, I just put, um, yeah, so I confused this orbital notation with the electron shells, right? So orbitals are not the same as shells. And so once I knew that, I was a bit more confident. I learned the 2, 8, 18 um, kind of thing that works well for like the first 20 elements or so. Yeah, so cleared that up. Yes, so just a bit more of these counting with valence electrons, and then which molecules per taken? Yeah, I just another pasted question, um, another pasted question, another pasted question, just to clarify some of these concepts, and then I uploaded this question as well. And interestingly, here the model had a loss, so I asked it how many valence electrons are present in this molecule. And it says 36, but the answer key is 38, and 38 is the correct answer, but it misidentifies this compound as cyclohexane for some reason instead of just regular hexane, which is what it should be. This is not a closed loop, nor is it. Oh yes, sorry. Yeah, if this was bonded together, then it would be cyclohexane, but it's not. It's just a straight chain here. And so originally it gives me a incorrect answer. It's a loss. I like clarify it, and it actually like acknowledges the error. So that wasn't very helpful. Actually, I feel like I just realized that I was a bit confused by this response. And then I asked a bit more, some clarifying questions about that benzene question, about properties, what would it be classified as, what's special. And it gives me delocalize as well after pasting in the question. Asked about aromatic, and then in the end, I also tried to clarify. I tried to get it to make me some tables so I could really quickly take in some information about different functional groups for organic chemistry. So I asked about carb acids, alcohols, everything like here. I listed them, and then it tells me some of the forces. I feel like this was like a bit, this is slightly helpful, I guess, for just refresher on how to identify each of these functional groups. And then a bit more clarifying conceptual questions on boiling points. I asked it to rank the strength of the forces and thus their boiling points. And then I asked one of the last questions. Okay, yeah, I asked about titration. Yeah, I asked about titration because I was a bit thrown by that last question here. With the 2 titration, I was thinking, when would we use titration? But yeah. Okay. And then here is where I started the what is it? The guided study session with these kinds of questions. I do remember I had around half of my time remaining, so I'm just going to do a 7-minute timer and just, I guess, leave off exactly where I was. So I asked it these questions that were listed. So what was it here? First question, second question, and I was on the third question, I believe. Oh, I asked it about recovering my original recording, but okay. I just finished reading through the second question here, and then I was moving on to the third one. Actually, I think it was like closer to like 8 minutes. I'm just gonna put that and get the timer started. Okay, so it gives us this answer. Let's read through. So, okay, yeah, so this is just a question that tries to help us clarify intermolecular forces and how they influence like boiling points and their strengths. I feel like I understand this concept pretty well. Like the big three here. Ethanol, decane. Yes, it makes sense. Decane would be higher boiling point because it's a massive molecule, whereas ethanol is smaller, and although it has hydrogen bonding, it's beaten out by the force of the LDFs. Yeah. Next question. This next question is an interesting one. What case can LDFs vary, right? If their molecular formula is the same. I don't actually know. Isomers, right? Yeah. Chirality. Okay. And so, okay, let's read through. Oh, okay. So it's about surface area. Surface area contact. Okay. This is a bit of a nuance that I'd forgotten. Branched compact molecules are more spherical. Okay. Cannot get close to each other. Is this correct? Because I feel like long straight chain molecules would have less surface area contact, and the branch ones would have more. Okay, so straight chains are higher boiling points. So straight chains, like more simpler molecules that cover a bigger area, are higher LDFs, while branched ones are lower LDFs. Okay. That is good to know. Okay. How do I count valence electrons in an alkane by looking at the carbon skeleton? Oh, okay, yeah, this is a good question. This was just the concept that I struggled with my first pass through of this quiz. But yeah, this should be, 6n plus 2. That's a nice little general solution they give us here. For a non-cyclic alkane skeleton. Okay. So for a hexane molecule, it was 38, right? So 6 carbons times 6, 36 plus 2 is 38. So that does check out. 6n plus 2. That's a nice little shortcut there. I might use that one instead of counting the individual ones. Okay, yeah, that's good. Last question. How can titrations used to be? I feel like I asked it a very similar question here. How is titration used in identification of molecules? Okay, so it's going to give us very similar, um, extremely similar response. I don't know how useful this response is to us because it talks about like pKa calculations, right? And this kind of thing, which we probably won't have to use in this OChem test. I mean, this is all correct, but this doesn't particularly help me that much. Chemical fingerprints. So I guess, is it acid strength? Okay. Okay, I guess if we were to be given a mystery molecule with a that was not neutral, I guess we would just look at the pH and determine and just go from there. Okay, that's good. I'm pretty much done with this guided tutoring session. Let me just reset it here, get it back to 15, and then complete the quiz section. This is just the PDF quiz here. So I'm just going to download it, upload it to the model. Actually, just going to put that in. Okay, I'm just going to start here. Start on this session. I believe Gemini gives us a. Oh, it doesn't. Okay, this is weird. Gemini doesn't give me the quiz function. When I did the biology one, I was given. Oh wow. Okay. Try. Maybe a different function. Will it give me the pop-up quiz thing? Okay, no, it won't. Okay, so I guess I'll just go through how many questions it gives us here. Oh, okay, 5 short answer. That's okay. Okay, so let's go through here. 5 multiple choice. I'm just gonna go through. According to the diagram on page 1, numbering the parent chain of the molecule should begin at which carbon? Oh, it's giving me. Okay, so it's going to reference this. Okay, that's odd. Okay, numbering the parent chain of the molecule should begin at which carbon? Okay, hold on. Let me look through this. Let me look through this sort of quiz that Gemini's given us. This is it just wait, what is this? Okay, so Gemini has done sort of not a very helpful thing here. I think they've just ripped questions directly from the file. Like this is the same question. This is the same question. 2 is the same. 3 is the same. 4 is this. These are just all the same questions from the quiz that I just did. And same with the short answer as well. So this is not normal. Like these are all answers that I got. Okay. I guess there's no point in doing the quiz again, but I can try and ask you to regenerate stuff. These are just all the same questions again. This is not very helpful at all. I'm not going to do the same quiz again. Let me see how it behaved for biology. Okay, like it gives this quiz for biology. Okay, let me ask it something. Let me try and, can you make new questions that are similar to the one from the file, and present them with quiz format? Okay. Okay, so it doesn't give us the okay. It doesn't give us exactly the quiz function, but I guess this is fine. We'll go through really quick. Okay. Grade my quiz. 1. Highest boiling point. Okay. So propanol, diethyl ether. Not diethyl ether. Not butane, so it's either propanol or propanol. I'm not sure where is this a ketone? No, this is an aldehyde. I'm not sure where aldehydes are classified here. Maybe I'm just gonna put propanol. I'm just gonna put the letter, yeah. Characteristically fishy odor most likely contains which functional group? Fishy? Be like ammonia smell? Amine? It's not ester, because ester should smell sweeter. It's not alcohol. So it's either ketone or amine. I'm just gonna put amine. I don't know too much about ketones actually. So the following substances would be most likely to dissolve in hexane. Hexane, okay. So water's polar, hexane's non-polar, so it's not going to be that. Methanol is polar and hexane's non-polar. Carbon tetrachloride is non-polar. And sodium chloride. Okay, yeah. We're just going to put C. Tetrachloride, like dissolves like. The exceptional stability of aromatic compounds like benzene is primarily due to delocalization, right, of the pi electrons. We studied that. They don't have high molar mass. They don't have hydrogen bonding. And the shape of the ring, maybe it's the shape of the ring. I think it's the electrons. Okay. Ethane, how many valence electrons? Okay, this is a good opportunity to test out our 6n plus 2 formula. So 6n plus 2 here would be 14. So, but just to be safe, let's just count. So 6 plus 8 is 14. So yeah, that is correct. A lot of C's. Short answer. Okay, so this is just asking us for some new naming. Since ethyl is alphabetically before methyl, we're just going to do 4-ethyl 2-methyl 7. Explain why propanol has a significantly higher boiling point than its isomer. Methyl ethyl ethyl ether. Okay. Why are esters... Wait, is this even an ester? Huh. It's curious. Okay. Explain why propanol has a significantly higher boiling point. Okay. Okay, because of the more branched nature of the molecule structure, no, it should be chained, maybe for the molecule structure, which strengthen the effects of the LDFs compared to the isomer, which may have less surface area for electrons to interact. Additionally, propanol being an alcohol has dipole-dipole and hydrogen bonding forces. 8. 2 isomers. Which is the higher boiling point and why? Okay. N-hexane. Okay, so N-hexane and 2,2-dimethylbutane. N-hexane. Because its LDFs are stronger, as it is a more chained molecule compared to the more branched isomer. You have 2 unlabeled vials, pentanoic acid, one containing an ester, ethyl propanoate. Huh, okay. Besides smells, other simple tests involving water and pH paper. Okay. Water and pH paper. Okay. Okay. Pentanoic acid. Pentanoic acid being a carboxylic acid. Have a higher pH compared to a lower pH compared to the ester. The acidities could likely distinguish the molecules. With the water test, I don't know if ester is polar enough to dissolve in water, but I'm just gonna put that, yeah. Dissolve compared to the ester. I'm not too sure about that one, but I'm just gonna put it there. How many hydrogen atoms are in one molecule of heptane? Heptane, so C7. So 7 times 2 plus 2 is 16. Okay. And then I'm just going to ask it to mark me. 16, yep. Small amount of water. Ester is much less soluble. Oh, okay. This is good. N-hexane, yes. Propanol could form bonds. Weaker, yes. Methyl octane, yes. CBCCC. Oh, okay, so I got. Oh. Partially correct. Okay, 7. Only 7. Propanol can form strong hydrogen bonds. What did I write? Propanol has. Oh, okay. I should have focused more on the hydrogen bonds part. Okay. So what did I get? Correct, correct, correct. 0.5. Correct, 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 correct. Okay. So 9.5 out of 10. That's okay. I guess we'll just cut it a bit short here with our quiz section, but that's fine. Okay. Take a break and then the post-test. Okay. Post-test time. Okay, yeah, sure. Let's see the post-test. I'm gonna keep my results here. Chemistry A, okay. Okay, we're gonna start the timer here. Oh, wow, okay. How many carbon? Okay, parent chain. Let's begin counting. 1, 2, 3, 4, 5, 6. 1, 2, oh. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I'm missing something here. 6. There's clearly 6. 3, 4, 5, 6. It can't be 5. 1, 2, 1, 2, 3, 4, 5. No, it's 6. 6 hexane. I'm bringing this molecule. Okay. So alpha and delta. 1, 2, 3, 4, 5, 6. 1, 2, 3. 1, 2. It's going to be 2. So 1, 2, 3, 4, 5, 6. Oh, wait, hold on. Is it 1, 2, 3, 4, 5, 6 or 1, 2, 3, 4, 5, 6? No, it can't be. You can't just cut out. Yeah, okay. This is going to be alpha, because this is 2 versus 3 here. 1, 2, 3 versus 1, 2. So it's X, going to be on X. Branches on carbon X are called cyclopropyl and methyl. That seems right, yeah. This is a large type of branch that's common between X and Z. What is it called? Type what? There's a type of branch that's common between carbon X and Z. There's a type of branch that's common. X and Z, not X and Y. Okay, X and Z. So what do they have in common? 2 methyl groups, 1 methyl group, 1 cyclopropyl group. So it's going to be methyl group, right? Which carbon is able to make another bond? So not X, Y can. 1, 2, 3, 4, not Z. So it's going to be Y. Is it? Yeah, 1, 2, 3, 1 more. Can do 1 more on Y. Which carbon is able to, okay, yeah, which of the IUPAC, oh wow, this is going to be extensive. Okay, so cyclopropyl is pretty far ahead. So 2 cyclopropyl 2, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. On carbon 4 and carbon 2 is the methyl group. So 2, 4, 4 trimethyl. 2, 4, 4 trimethyl. And then the last group is the propyl, right? 1, 2, 3 on group 3. So 3 propyl hexane. 2 cyclopropyl, 2, 4, 4 trimethyl, 3 propyl hexane. It seems right. Maybe there's some sort of alphabetical order kind of thing that I'm missing here, but that seems like it's right. The addition of a methyl group onto carbon what would cause a change only to the name of the parent chain? Oh, okay, so we're looking for either alpha or delta here. Oh, actually, hold on. Methyl group onto carbon. What? Okay. Oh, okay. So we're asking, I think it would be delta. Yeah, it would be delta because if you change it on alpha, then it becomes a question of which one is the first carbon, and that could change the entire name of the molecule with the direction. But I think it should be delta because methyl group on delta, yeah, I guess it just lengthens the chain, keeps the same naming convention because alpha is still here, and you just call it heptane instead of hexane. Okay, not an organic molecule. Tetrafluoromethane. Benzene, hydrogen cyanide. I think this is an exception, right? Cyanides are the exception to organic molecules. It could be butoxide, but I'm seeing bute, so I'm just going to put a hydrogen cyanide. Valence electrons in butane. So butane has 4 carbons. 6 times 4, 24. Plus 2 is 26. Let's just verify it. Butane has, its chemical formula is C4H10. So 4 times 4, 16 plus 10 hydrogen is 26 indeed, so 26. Which element has the same number of electrons as butane has? Valence electrons. Okay. Same number of electrons as butane has valence electrons. Okay. Huh. Okay, so, oh, okay. This is just a, oh, I don't know this, unfortunately. I don't have a periodic table. Something about the properties, maybe we could tell. Same number of electrons as butane. Are we supposed to have access to a table for this? I don't think it's, these are all tough. They're all in like a very similar area, so it makes it annoying. I think iron is further down, is it? Maybe it's one of these two. I'm not sure. I guess I have to accept that I won't get this correct because I don't know. What is number 26? 26 sounds more like a nickel or a zinc to me, actually. I don't know. Maybe we'll come back to that one. So the following functional groups is most likely to emit a pleasant sweet smell. The ester here. The answer. Oh, actually, can it participate in hydrogen? No, the ester. Okay. No, the ester cannot participate in hydrogen bonding because it doesn't have the required functional groups which allow for that to happen. Wait, sorry. The required polar groups, OH, NH, what else is there? F? I don't think it's F. ETC. I'm just going to put ETC. You put ETC when you don't know what to say. It might also depend on the functional group R. Depend on the R group of the ester. Which molecule will have the highest boiling point? Okay. Okay, so it's between these two. Is this an ester? Hold on, COO and then CH3. Yeah, okay. So I think it's going to be carboxylic acid here. Because of the hydrogen bonding, dimerization, as well as the, what was the last part? Hydrogen bonding, dimerization, and dipole. Yeah. How many hydrogen atoms does alkene with N carbon atoms have? It's going to be 2N. Okay. Which molecules have LDFs? All of them. Every molecule has LDFs. Each substance is a liquid at room temperature. Which of these molecules can mix with water? Okay. Which can mix with water? Okay. So water is polar. Decane is not polar. Ethanoic acid is polar. Heptene is not polar. Ethanol is polar. So it's going to be ethanol and ethanoic acid. Yes, because they're both polar and polar mixes with polar. Okay. Ethanol and ethanoic acid are both polar molecules as a result of the OH group they contain. Water is also a polar molecule based on its structure. I don't know. Like dissolves like. So these two polar molecules successfully mix with water. Looking from the case of intermolecular forces, these molecules mix, in the case of intermolecular forces, these molecules do what? Are also alike with all three compounds containing LDFs, dipole, dipole, and H bonding. Decane does not have permanent dipole. Its boiling point is much higher than ethanoic acid. Well, decane contains the most carbon atoms. These are both wrong. Unstable? I don't think so. Most carbon atoms, LDFs. Simplest response, I think. Yeah, this is a massive chain. This little 8 of the CH2 chain there. Where would you expect methanol to place on this list? Okay, methanol. So methanol would place below ethanol. Certainly below ethanol, because it's just this is very similar alcohol but just smaller. So oh, there's nothing between, so I guess just below. Oh, what? Methanol above ethanol? What? Oh, above ethanol. Okay, yes, I thought it was saying here, but okay, yeah, that makes sense. Above ethanol. Okay, we have 1, 2, 3, 4, 5 cyclopentane here. The addition of a methyl group to which carbon would not produce a molecule with a side chain? Addition of a methyl group to which carbon would not produce a molecule with a side chain? Methyl group to which carbon would not produce a molecule with a side chain? All of them. Because it's already a closed loop. It's already pentane. Doesn't matter which one you add. It's just going to be symmetrical either way. Yeah. The addition of a methyl to which carbons would produce the same molecule? All of them. Because, yeah, it should be all of them. How many valence electrons are present in this molecule? Okay, so the formula for this cyclopentane should be C5H10, right? Because even though there's no double bonds, it being cyclized means that you remove two of those hydrogens. So instead of C5H12, it's going to be C5H10. And so 5 times 4 is 20, plus 10 is 30. Yes, okay. Yeah, that works. What is the maximum number of propyl groups that can be added to carbon A? Okay. 2. Oh, actually? Yes, 2. Is it 2 or? Yeah, it's 2. The electrons in the benzene molecule are not fixed on one atom. They are delocalized. This is a bit of a shill question, isn't it? Because it's the exact same one as the version B. So students are like, who get this wrong are confirmed to get this right. Acidic flavor compound naturally dissolves in organic. Okay, it's nonpolar. It's not this. It's not polarity this time. Does not have any natural odor or color. Acidic flavor compound. Naturally dissolved in organic solvent, nonpolar. I don't think the dye will help either, but okay, just because we're given the pH being acidic, we can just because the pH is acidic, I guess titrating with NaOH will help because just going to change the pKa, titration curve, whatever it is. NaOH, very strong base, will neutralize the acidic solution. Adding just more acid won't really help. Decreasing the pH past 0 is just unnecessary. I don't know if HCl is even strong enough to decrease pH past 0. Maybe it is in high enough concentration, but yeah, I think that makes sense. So we finished a bit early actually, 3-4 minutes left, so that's good. I guess I'll just check over the quiz. Okay. Two, three, four, 1, 2, 3, 4, 5, 6. Yes. 2, 3, 4, 5, 6. But you can't do this because this is not a chain, right? So 1, 2, 3, 4, 5, 6 works. 1, 2, 3, 1, 1, 2, 3, 4, 5, 6, 7, 8. Imagine. Carbon A, yes, 2 versus 3. I'm still like, maybe I misunderstand this question. Addition of a methyl group onto carbon blank would cause a change only to the name of the parent chain. Okay, it does make sense because if you add it onto alpha, does it make delta carbon 1? Because, this is odd because how, if they have chains on 2 and, on 3 and 3 for both sides, then how do you determine which is carbon 1, right? Maybe it's like some alphabetical thing then, but I'm not sure. But it wouldn't change anything if you just added onto delta. That seems completely fine. Okay, I don't know about this though. 2-cyclopropyl, because C is first. C is the third letter. This is not, we're not looking at the T, we're looking at the M here, right? So 2-cyclopropyl, 2,4,4 trimethyl. So 2, 3, 4, and 4. Trimethyl, yeah. Trimethyl 3 propylhexane. 1, 2, 3 propylhexane, yes. It looks right. And again, I'm not sure if this is the correct exception. I do understand that there is hydrogen and then there is cyanide, because cyanide is CN, but maybe in this case, the hydrogen's bonded to the nitrogen instead of the carbon, so that's why it's invalidated. I do particularly remember, though, cyanides are not considered organic molecules. I've been taught that so many times. Butane 6N plus 2, again 24 plus 2, yes. Okay, this one, oh my goodness. Am I being just silly? Should I know like the groups or like... Oh wait, maybe I can deduce by what they bind to, yes. Hold on, so what do we have? We can do like iron binds with, or actually, zinc and nickel chloride, so seven valence electrons. Iron Fe is not, so these are, okay, if these are in the same one, then I don't think it's, so it might be chromium, because, wait, can you have zinc chloride? I don't think so. You can't have, wait. Oh, this is odd. Okay, I'm just gonna stick with nickel. I don't know. CR chrome. I don't know. We're out of time. We're just gonna go ahead and submit. What do we get? 21. Darn. Okay. Oh no. What? Oh my god, it's an ethyl group. Wait. Oh my goodness. That is so sad. That is incredibly sad. I thought this was a propyl group because 1, 2, 3, but it should be 1, 2. That is such a shame. Oh my goodness. And this is iron. Wow. Just my luck. Okay, maybe we get these. No, not bonded. Yes. I think this should be marked right. Why can they mix with water? Both participate in hydrogen bonding. Yes, like dissolves like. Okay, so I think I should get that marked too. Okay, so what is that? 23? Wow, that's such a shame. What a stupid mistake for this molecule. Ethyl instead of propyl. Okay, yeah. And just like I just had to have a periodic table for this, I guess. Or maybe if I just thought harder as to like some of the compounds that these metals form, I could have gotten it, but I guess I didn't have time there. But that does make sense. Yeah, just what a shame. What a shame. Okay, cool. Sorry for like spacing out, nerding out over the quiz after submitting it, but I think my score improved by, so the first time we got, what is this, maybe 19 or like 18, and an improvement to 23, so I think that's pretty okay. That's without a shortage of faults from Gemini at the same time though. Recall that we had some issues with the generation of the quiz. I had to feed it a custom prompt in order to, yeah, here, new questions, make new questions, in order for it to completely correctly generate questions, but, and also it had some losses. For instance, it said, what is it? It identified cyclohexane, right? But this is clearly just hexane for during the study period. And so it's just my apologies for the error. So it definitely does somewhat confuse. Luckily, I like overlooked it, but overall, yeah, that is my results for the chemistry portion of the AI efficacy study. And then all I have to do is complete the surveys. Okay, cool. Thank you.